Good morning, everyone. And Marco, you can hear us well?
Yes, loud and clear.
Perfect. And you can see us or see the slides at least?
Yes, perfect.
Perfect. So thank you everyone for joining, Gabe Margolis's, PhD defense today. Uh, so I guess I know Gabe for quite some time now. And I think a prelude to how Gabe ended up in the lab is I was coming to MIT in 2019. And before coming to MIT, I was having conversations with, Mark Rybert, who I guess is the founder of Boston Dynamics. And they had their Spot robot, which was very, very mature. And I wanted robots for my lab. So I went to Mark and said, Mark, can you give me a robot that we can use? And I think Mark told me that um, if you only want to do, high level planning and make the robot go around, I'll give you a robot. But if you want to touch the low level API, that's something that no one should do because, control is pretty stable and pretty robust on that system. So, and all I wanted to do was low level control on the robot. So then we went to Sangbei's lab and said, Sangbei, can you give us a robot? And then Sangbei handed us the mini cheetah. And ironically, in the same week, I think Gabe emailed me saying that, "Hey, I'm a Europe looking to do research in a lab." And when he walked in, I had like, "Hey, Gabe, I have this MIT mini cheetah. Do you want to do something fun with it?" And our lab had no experience working with legged locomotion before. So Gabe helped establish, pretty much from scratch, the entire legged locomotion stack that we ended up developing over the years. He showed that reinforcement learning trained from sim to real can be a powerful tool and added to the growing body of work to show that we can get, very agile motions. And in the later part of his thesis, thinking a lot about contacts and what's missing in humanoids today. And a lot of the world today is in this mode where they think that vision to actions is all of manipulation. But actually, forces is a language of physical interactions. And I think Gabe has been breaking that barrier once more to show that, forces are going to be the right way forward. Um, Not only, Gabe has written a bunch of very nice papers, but also he's always been there as a mentor to, many students in the lab. At some point, the locomotion lab was like 7 or 8 students, with Gabe mentoring all of them. So we have had a lot of fun, whether it is inside the lab, whether it is going on treks on mountains to take a dog or robot dog over there, or whether it is taking a robot to New Zealand. And probably the most one of the more popular ones was in RSS, when there was a cruise ship that we were going around and there's a disco happening. And then we demonstrated the robot dancing in that disco. Um, so it's really been amazing to have you, Gabe, as part of the lab, not just with the research breakthroughs that you have made, but also being very, grounded in research, where it is very easy to get very hypey, at least when we think about robotics and robot learning today. And for also mentoring many students who are now pursuing their PhDs or have started companies. Um, and with that, really looking forward to your talk.
Yeah, thank you so much, Pulkit. Uh, yeah, so thank you everyone for coming to my PhD thesis defense. Today, I'll be talking about my work on learning intelligent contact for dynamic robots. Oh, I didn't know that. Okay. So right, why contact what is intelligent contact and why is force important in robotics? So to motivate this, I'll actually take us back all the way to the 1980s at MIT and to a few different projects that were being done at that time. So one that's definitely famous in robotics history is the Vibert Hopper from the MIT Leg Lab. So this was a robot that just had a single leg and it hopped around in order to get from place to place. And what's interesting is that, you can imagine a wheeled robot, if you want to go forward, you just spin the wheel. But for this robot, there's no actuator that will just take it forward. It's under actuated. So the only way for it to move around is to manipulate the direction and magnitude of the force that's being applied through that leg. And a second way that force manifests in robotics, also has its roots at MIT in the 1980s in impedance control. But here's a more recent video from 2008 at the DLR, German Aerospace Center, a robot arm being tested against a crash test dummy. And the question is the robot arm aware of the force that it's applying or not? So if it's not aware, the crash test dummy will have quite a bad outcome. But if you design the controller in such a force-aware way, instead of crashing through the test dummy, it can just bounce off. So I think these epitomize sort of two roles of force in robotics, one being used for dynamic control, and the second being safety and generalization. And if we look at the capabilities of humans and what they do in their workplaces and out in the wild, they're masters of forceful manipulation. So here are just a few examples. So these workers are accelerating and then maintaining the momentum of this bucket to pass it up a ladder. Here's a assembly line worker who, instead of picking each item, is flicking them into the bin, and he's able to do the task much faster. Here's a man pouring ketchup into little ketchup baskets, and there are, I think, two interesting things. First, it needs to apply a certain amount of force to pour the right amount of ketchup. But second, as the box gets lighter and lighter, he needs to also adapt how he's doing the motion. And finally, here's more of an example of force understanding in a scene, but you might have some creative ways of doing tasks by manipulating forces instead of just picking and placing objects. But in contrast, if we look at the robots that are actually deployed in factories, since the 80s to today, you'll probably find a lot of robots like this that are essentially force unaware. So they're capable of applying large forces, but they don't receive any feedback about whether they are or not. They're simply position controlled. So all you can do is command the robot to go to a position, and it'll try to do that no matter what. And if something gets in its way, one of two things will happen, or might be likely to happen. Either the robot will break something in its surroundings, cause damage, or it'll damage itself. And so finally, let's fast forward to what is the frontier of robotics today. So really, I think in the past decade, we've seen the rise of this paradigm with data-driven learning in simulation. And these are just two examples from right before the start of my research career. So there was this in-hand reorientation demo from OpenAI in 2018, where they trained the robot, this robot hand, to reorient blocks in sim, and then play it on the real robot. And then here's one of the seminal works in learning locomotion from 2019 on the Animal robot from ETH Zurich. So similarly, they train the robot in the simulator, and then so they train for walking around and also getting up motion. And then the same capability can be played back on the real system, and it can respond to kicks and operator steering. And one thing that's really critical to understand about this data-driven learning is that it's different from the way that the other control systems that I showed you before were designed. Instead of sort of programming how the control loop should respond to different types of inputs, the control strategy is learned from experience in the simulator. So I'll just add a little bit of color to that. So here's an example of a simulator that we used in our lab, simulating a small quadruped. So it can simulate thousands of robots in parallel. And what the way the training works is you have some control policy that's a randomly initialized neural network. So at the beginning of training, it doesn't know anything about how to solve the task. And the inputs to the network are the observations from the simulator, and the outputs are actions with a little bit of exploration. So the way the training proceeds is the neural network, it interacts with the simulator, it aggregates some experience, and then we use a reinforcement learning algorithm, like policy optimization, to update the network, essentially weighting actions that lead to higher returns more strongly and downweighting actions that lead to lower returns. And continuing through the works in the past, like sort of data-driven era, especially for locomotion, towards the start of my PhD, I was also working a lot on enhancing quadruped capabilities through this sim-to-real approach. And so some of the first projects that I did were, I'm only going to briefly mention them today, but we trained a fast running policy on the MIT Mini Cheetah that was the first to sort of surpass the maximum speed obtained by analytically designed controller on this robot. And at the same time, it was also robust to various different terrains where the baseline failed. And a second project that we did was this robot soccer project. So we trained the robot instead of controlling its own velocity to control the velocity of a soccer ball. And we trained it on all sorts of randomized terrains, and it was able to learn to take the appropriate actions to manipulate the soccer ball with its feet while also walking and running. And so these are some autonomous rollouts where it's just dribbling out and then dribbling back. It's even able to do it on snow where it's simultaneously slipping and also trying to manipulate the ball. So, and just one more slide of videos, this is what we're seeing today, really the application of the same type of learning paradigm to humanoids. So these are videos from just, the past year or less from Boston Dynamics, which is now applying the same type of control strategies to Atlas to do all these athletic motions, and a similar video from Unitree. And so this brings me to kind of the opening question that for the works that I'm going to talk about. And essentially, this is sort of my thesis statement. So data-driven control, I think it's unlocked new opportunities and challenges for the type of force-aware control that I showed on the first slide. And we've especially seen, I think, its use to sort of control dynamic systems, but maybe less on the safety and generalization side. And as I will argue in the coming slides, force-first robot learning has the potential to make modern dynamic robots more capable, general, and safe. So what do I mean by a force-first robot learning system? Well, I'm going to provide 3 examples today. The first I'll describe is our project on learning force control and teaching this quadruped manipulator to control the contact force that it applies through its end effector. The second I'll describe is our work on active sensing policies that optimize the contacts the robot makes to actually communicate more information about the terrain. And the third is our work soft mimic, where we trained a humanoid robot to imitate human motions while also being force aware and compliant. So the first of these, learning force control, the key question that we wanted to answer is, can data-driven control explicitly sense and manipulate force? So yeah, back in, I think, maybe 2023, we had this platform. It's a large Unitree quadruped with an arm on top. And so we developed a controller that could both walk around and also move the end effector to match a teleoperator who's wearing the virtual reality headset capturing their wrist motion. And so this was sort of, I mean, an emerging but maybe known way of doing things at this time. So you'd have some neural network policy, and it would observe the sensor data of the robot and output actions, and it would also observe the desired wrist command that's supplied by some teleoperation rig. But during training, maybe that would be randomized. And our simple proposal, just to understand, what are the properties of training something this way, is to replace the position command with a force command. So instead of the teleoperator saying, go to this position, the teleoperator will say, apply this force. And that's especially relevant if the robot is, for example, pressing up against a surface like a whiteboard and needs to control how hard it's pressing, which might not be well described through just a position command. But the question here that we ran into is how can we train this? Because okay, the typical way of training would just be to have the robot walk around in free space. But if you try to apply some force in free space, the robot will never experience any external force, and the hand will just accelerate. And this, I think, really is the key difference that we need to think about in data-driven methods. We don't just need to define sort of the objective of the system and the model. The robot also needs to experience the types of interactions that we want it to be able to accomplish in order to learn a good response. So our solution was a method of virtual force fields. So what we did was we spawned a set point and everything, well, specifically the gripper was attracted to the set point with some force proportional to the distance. So it's essentially a soft contact model that we were emulating. And the set point walks around in space, and the robot doesn't observe its location. And it also doesn't observe the amount of force that it's applying because it doesn't have a specific sensor for that. Instead, it needs to feel its way through the force field based on the feedback that it's getting in its joints until it reaches the desired resistance level. And so by introducing these force fields, we essentially couple the robot's actions with a reaction force that it experiences. And so during training, we can now reward the minimizing the error between the commanded and realized external force to try to encourage the robot to learn this sort of feeling around motion. And yeah, we trained this policy, we deploy on the robot, and there's my collaborator Tiffany manipulating the end effector. So the policy is able to realize sort of this compliant control of the robot, where if a human grasps the end effector, they can move it around. And we also showed in this force control mode that we could do some very basic gravity compensation behavior. So we loaded up this canister with some bricks, and when the robot's commanded with 0 force, it'll just sink to the ground. But if we supply a force command that counters the brick's mass, then it'll keep it elevated while remaining compliant. So we can also still manipulate the canister through space without supporting its weight. And we also did some experiments with more details in the paper to measure whether the robot is really realizing these different force commands in the real world. And actually in this system, it was responsive. There was some error. We also found later that there was a bit of a symmetrical gap in this arm that was actually resolved in some future work. So another interesting thing we did with the system, so it's kind of interesting to control force, but it's not that useful as a teleoperator. Most of the time, you don't have that much intuition about how much force should be applied, and it's kind of unwieldy to command this through a joystick. So what we did was, on top of this force control policy, without any additional training, we implemented an impedance control loop where essentially we took the position of the end effector and compared it to the desired position supplied by the joystick. And then we computed the commanded force based on some stiffness parameter. So it's essentially just a Cartesian PD controller. And we have a damping parameter as well, but by manipulating the stiffness and damping parameters, then we could realize different types of compliant behavior in the robot's end effector while also controlling its position. So just to show a comparison, here we have sort of a position control trained policy that's receiving some ramping external force, and it just tries to stay in the same spot until it eventually tips over. But with our impedance control loop, we could see that both the robot reacted more naturally and compliantly, and also by adjusting the stiffness parameter, going from right to left, we were able to realize a different amount of displacement in response to that force. And so we put this on the real robot and teleoperated it in impedance control mode, and we showed that it can do some basic loco manipulation tasks, and even is capable of dragging a very heavy object. It's actually, I mean, I think this is actually a great example of where compliance really helps, because the robot's moving around. It's hard to keep the gripper in exactly the same spot, but there's really kind of a constraint in the system, right? If you try to push down through the chair or try to pull up through the chair, you're going to get a big reaction force. So it's important to have some compliance to achieve types of constraint tasks. So the second project I'll talk about to illustrate the role of contact in learning is this active sensing policies. And the main question we try to answer is, how can we optimize force interactions to gain information about the environment? So the setup for our experiments was, we were considering this scenario. Suppose you have an overhead image of some terrain like the courtyard outside of Stata, and you have some different options for paths that the robot could take. And you have also some different behaviors that the robot might be doing. So in one instance, it might be just walking, but then in another instance or operating mode, it might be dragging a payload. So if you think about sort of how these two different behaviors might respond to friction, I think it's somewhat intuitive that for locomotion, walking on ice is a bit hard, but for much higher friction terrains, they're all kind of okay. The robot's not slipping. But for dragging a payload, it actually, it matters if the friction is twice as high, because you are going to get more resistance from your payload that's proportional to the drag force. And so, yeah, you have this plot where the friction is, the mean velocity is remaining high for locomotion and then degrading for dragging a payload. And because of this, you might have some different preferences about which route you prefer to take across this terrain. So our idea was, let's go out, we'll mount a camera on the robot, we'll collect some traversal data. And then what we'd like is for the robot, based on what it's feeling through its motors, we'd like it to label the terrains with different frictions, like what friction it's feeling as it walks across. And then we'll use those labels to train a vision model that can predict the friction coefficient on new terrains and do planning. So, but there's a subtle challenge with this, which is that the inferences of friction are actually task specific. So what do I mean by that? So let's consider this to be the setting. So we have our policy, and it's learning in this training environment that's parameterized by the terrain friction, mu. Now, one thing that might be a common, well, this is a common thing in the literature and also kind of intuitive. We could add a estimator module that tries to predict the friction coefficient from the robot's sensory data as it's walking. And we could train this estimator using some sort of supervised loss, because in the simulator, we know the true friction. So we're training it to infer what the friction of the ground is. And then, during deployment, we'll just take those labels. We'll use those estimates to label terrains and use that to train our vision model. But right, here's the problem. So let's suppose you have these terrains with different friction coefficients. And now we might ask, what will be estimated when the robot is walking? But this is, as an example, we might see at lower frictions that 0.2, 0.4, 0.6, the robot will slip. But above 0.8, the robot walking will no longer slip. And because of that, there would kind of be no information about what to differentiate these different high frictions in the traversal in the robot sensory data. So the takeaway from this thought experiment is that passive labels may not be predictive for a new task. We might need to go beyond them. And so we proposed kind of a simple solution. In addition to training this estimator with a supervised loss, we'll take the estimates, we'll compare them with the ground truth, and we'll reward the policy for making accurate predictions. So in addition to being rewarded for walking across the terrain successfully, there would be an additional reward term that says, walk in such a way that I can accurately estimate the friction. And so this was the method we proposed in our paper. And what happened is the robot learned this gait. So if you pay attention to the front legs, it's actually sort of intentionally swiping its feet more than is necessary to just walk, or maybe even more than is efficient. But it's doing this to gain additional information. And if you look, these are results from sim, but we have real results that match in the paper. If you train the estimator just passively, you'll get this cluster of predictions around kind of the mean where you can't really tell what the friction is. And then sometimes you slip and you get a low friction prediction. There's almost no high friction prediction. But when you do this active sensing approach, the policy can learn to walk in such a way that you get these calibrated and more precise estimates across a whole range. And so we took that actively trained estimator and we deployed it on, we walked it across these different terrains, used it to label the images, and then we trained on top of a Dyno V2 backbone, patchwise friction predictor based on the local appearance of the terrain. And so the result, which we evaluated quantitatively, but also through this demonstration, we took a drone up, captured video of the, or just an image of the terrain, and then inferred the friction parameter and used it to perform path planning for these different modes of locomotion. And then we executed the plans on the real robot and found that things matched up with the prediction. So when walking, it was more efficient to take a direct route across the grass. And when dragging the payload, dragging across the grass was actually higher friction and slowed it down. So it was better to stay on the sidewalk. So the third project that I'll describe to motivate the role of force in this learning-based control is our most recent work, soft mimic, which is the main question we asked is how can we control the response to force interactions for whole body motion imitation? And for a bit of context, so motion tracking is a very popular approach for training humanoid robots. It's great because you can capture it's easy to generate motion data by putting a person in a motion capture suit, and they can sort of demonstrate for the robot what they'd like it to do, whether it be a dance or some sort of other like motion skill. And so that provides a kinematic reference for the humanoid robot, and then the robot is just trained again in simulation, but with the reward being to match the reference motion as closely as possible. And this has been shown to work pretty well for at least, maybe not so much for interactive tasks yet, but a lot of free space dynamic tasks like this dancing shown here. But right, one interesting question is why has it not been as successful in interactive tasks, or why are most of the demonstrations operating in free space? And so as a thought experiment, let's think about this robot that's doing a T-pose. This is just a reference motion. So yeah, reference motion shown in blue is sort of going to be our notation for the section. And then, we could train the robot to imitate this and deploy it. And it does the same thing. Great. And now let's consider what happens when we put the same robot next to this Lego tower. And, we hit the start button and this happens. So the question is, what will happen next? And what I will argue is that it's useful to think about this force that's going to occur. And so some questions that are especially relevant are, can we actually detect this force in the sensor data of the robot? The second thing was, did the robot experience this type of force during training? Because if it didn't, then it won't know what to do. And finally, what was it actually trained to respond with when it sees this type of scenario? So, unfortunately, what we saw is that in sort of the existing standard way of training motion tracking, the robot will be very stiff, like that robot arm you saw at the beginning, and there are many kind of undesirable failure modes that can happen. So, if there's a rigid wall, then the robot on the far left just pushes itself out of the way and kind of stumbles. If there's a delicate object, the robot applies a large force, but instead of it being pushed out of the way, it could break the object. And a third failure mode is in simulation, a robot is trying to pick a box, but it's a little bit misaligned from the box. So it just experiences a really big reaction force that causes it to stumble back, and on the real robot would potentially cause an emergency stop. So, but why do existing methods end up this way? Well, if we think about the motion imitation setup that I described, what we do is reward motion tracking for some reference. And then, to make the robot robust, or like to either the symmetrical gap or to various disturbances, we typically apply some random external forces. But what you're really telling the controller to do in this case is remain in the same posture regardless of how hard I push you, which is essentially the definition of stiff control, right? So if we think of, now the relationship may well be very nonlinear, but if we think of it as a linear relationship between force and displacement, so the stiffness is sort of this coefficient that modulates this relationship. And so if you have a high stiffness, what will happen is even if the robot gets displaced a little bit, it'll try to apply a huge reaction force. And this might be okay if you're operating in an environment where the external force is constant. For example, you're carrying some object and the dominant force is the gravitational force that's pulling down. It doesn't really matter if you lower or raise your hand. But if you hit some sort of environmental impedance, like a wall or another type of constraint, like a box that you're squeezing, then the displacement can be forced to become large. So at that time, it could be really bad if you're training your policy with this bias to stiffness. And so what we did was we introduced this way of training a compliant whole body controller. So the idea is simple. In addition to these two rewards, we'll add a force displacement reward that essentially tells the robot to be compliant. And as in the first project that I described, we'll train the robot in these virtual force fields so that its actions can affect both the force it experiences and its displacement. And we'll condition the policy instead of on a specific force. We'll give it the full motion reference plus a stiffness command, K, that tells it. So the higher the stiffness, the less it should yield to external forces, and the lower the stiffness, the more it should yield. But there's some challenges with just saying, okay, let's set up the problem this way and train it. The first is that these two reward, we've essentially defined two reward signals that are in conflict, right? So one of them is track the original motion. The other is to match this force displacement relationship and be displaced from the original motion. And so when we're training the policy, these two rewards are essentially just going to be competing with each other, which can produce unstable training or undesirable, like hard to predict outcome. A second challenge is that doing this kind of breaks some machinery that is useful for doing motion tracking. For example, to track challenging motions, it's very common and sometimes necessary to use early terminations when the robot gets too far from the reference, and also to initialize the robot at the reference posture. But both of these will kind of it's not possible to early terminate if you have a second task that says actually you should be displaced as by a certain amount. And so when we remove these broken machinery, then a problem that happens is the policy can get stuck in local optima. So this is just something that's known for motion tracking, but it adds an additional layer of complexity to our compliant formulation. And finally, maybe I would say as a result of these two factors, when you try to train the policy like this, it could be very sensitive to the way that you tune the coefficients of these different reward terms. You kind of have to redesign how you're doing things slightly different from the standard motion tracking setup. And so the policy could easily get stuck in an example of being stuck in a local optimum is the robot on the far right that doesn't really learn to bend its legs and just leans in the direction of the force, which won't work for larger forces and also just looks less natural. So, to resolve these challenges, we rethought a little bit about how to approach this problem. And the reframe is, what if instead of trying to balance everything with rewards, what if we had examples of the robot complying in the desired way to external forces? So if we had that, we could make the motion tracking reward, instead of saying track the original motion, we could tell the robot to just track the whole body compliant reference. And in this case, there wouldn't be any more conflict between these rewards. All of the standard motion tracking machinery could just be used as is without any tuning. And the whole body behavior would also be explicitly specified. So if we want the robot to bend down, we could give a motion example of the robot complying by bending down. But a problem is, how can we get this data? Because if you just have a human motion capture data set, it's not going to have external force information. And it's also not going to have any notion of where the human wanted to be. So this is kind of, there's currently no way to get this from just recording humans. So instead, what we did was we generated some guiding examples, just using some simple heuristics, solving an inverse kinematics problem. So we set up our problem with constraints on the robot's feet and also the link that experiences external force. And then since this is a process that's not learning based, but just sort of solving some equations with a very fast optimizer, we can tune the parameters to obtain the types of compliance that we want. For example, prioritizing being near the original position in joint space versus key point space. And before we train the policy, we can actually play back this whole data set and make sure that it's demonstrating the type of behaviors that we want. And once we have this data set, then it becomes much easier, essentially just a standard motion tracking problem to train the RL policy to reproduce the compliant examples. And so this is the full training setup. So we have our policy that's learning in simulation, and the key is that it's observing the original reference motion, but it's being rewarded for tracking the compliant example. And because of this, we don't need to run any sort of IK solver online when we deploy the policy. The policy is handling everything. So it's handling, first of all, inferring the external force or displacement that's been enforced on it. And then second, it's learning to infer or reconstruct from that the compliant example or match as closely as possible how it should move in response to be matching this data set. And so so the policy is handling both proprioceptive force estimation and deciding how to respond. And when we train the policy and then deploy it, we get this nice compliant behavior. So this is just the robot standing in place. And so the reference motion is in blue, but there I'm grasping the hand and manipulating it around. And it lets me even pull it down and bends over. And when we compare it to sort of non-compliant ways of training, as well as training without data augmentation, we find that our method gets the best performance in terms of adhering to desired stiffness levels, even down to being much more compliant. And yeah, prior works trained with just stiff tracking have sort of much higher effective stiffness. And yeah, our policy is conditioned on the desired stiffness. So when we condition it to be very compliant, it's easy to pull around. When we condition it to be very stiff, it'll resist and behave more similarly to those original types of policies. And these are just a few video demonstrations of some ways that this is useful. So in this example, we have this box picking reference motion, and the robot bends down, but the box is not in the right spot. It's a little bit misplaced. So in the previous videos that you saw, the robot would apply a big force and stumble back. But in this case, it's learned to gracefully move out of the way. And it wasn't explicitly trained on like misplaced boxes. This just emerges from the sort of generalized compliant response as an objective. But then when the box is in the correct spot, we can also see that the same exact reference motion is able to pick multiple different boxes without either over-torquing the robot or damaging the box. And in that original example of doing the T-pose, we find that the compliant robot is able to detect that force or the constraint that it's not able to move up. And then instead of smashing through the Lego tower, it can just sort of gently tap it and then without damaging the environment or the robot. And we also just did some simple manipulation demo where it's pouring sand out of this bottle, and the stiff policy reacts poorly when its hand is forced down, but the compliant policy can move naturally. And finally, this isn't just limited to standing in place. We also showed that we can learn compliant control with a walking reference motion and other types of motions. So in free space, the robot's able to walk with the same quality as before, but when it needs, when it's dragging some object, it is also able to sort of let its arm wiggle around without nudging the object up and down aggressively. And this even works for a human-robot interaction where the force might be sort of unpredictable and irregular. Yep. And so, in conclusion, to summarize, sort of, I presented these three different projects that are all kind of tied together by the idea of doing better learning with forces. And what we could see is that by better considering the way that the robot handles external forces in data-driven policies, it can respond better to humans, it can better understand terrains, and it can interact more naturally and gracefully with objects. And so to summarize my argument again, like we've had these sort of compliant controllers for a long time, but the shift to data-driven control has unlocked both new opportunities and new challenges in this space. But I think that if we do this type of force-first robot learning, continue to develop it, we can make modern dynamic robots more capable, general, and safe. But of course, I'd like to talk a little bit about some of the limitations in future work that are associated with these projects. So in the compliant motion augmentation, we're using this IK solver. It relies a lot on heuristics, and it's still an open question how we can scale this to A, how well it works for very dynamic motions, and B, how it scales to motion data sets that are larger. And a second open question is that we have this compliance command, but right now it needs to be manually tuned based on the context. So could we instead adapt automatically or in a task-oriented way? And finally, in the active sensing policies project, this was really focused on estimating some specific parameterized simulator properties, but what about active information gathering with a broader family of candidate dynamics like a world model. Yep, so that concludes the technical part of my talk. I know I'm running a little behind, but I just have a few minutes of acknowledgements. Yeah, first, I'd like to thank all the direct collaborators on the projects that I presented, especially, Tao and Chang really mentored me when I was an undergrad. Ga and Kartik were collaborators on like the early mini cheetah work. Yandong was an awesome visiting student who led a lot of the loco manipulation. Tiffany wrote her amazing master's thesis on learning force control. And Nolan and Michelle have really spearheaded a lot of the humanoid learning that we've been doing recently. And of course, there are too many other collaborators to go through each one, but I'm definitely grateful to all the people I was lucky to work with in my time in my PhD, and also everyone in the lab. We've had some awesome times, lots of lab retreats, etc. So thank you for making it such a great experience. Also, all the friends outside the lab, especially folks from undergrad who I've known for a long time, and roommates, you really helped me, have fun and de-stress outside of work. And yeah, also my girlfriend Yujin, who I'm really grateful for, and it's been we've known each other since 2022, and she's best partner I could ask for. Really supported me in this journey, and also my mom, who's also here, and always really encouraged me to pursue what I'm interested in and do what I love. And also my dad, who's also here, and also my stepmom Zoya, and stepbrother Cyrus, and thanks for the support and love. And my dad, I think he really inspired me as an engineer and researcher to try to pursue positive impact and cool things. I'd also like to thank my committee members. Daniela, thank you for being on my committee. I remember during COVID, when I was an undergrad and master's student, you'd always come by my room where I was working on the mini cheetah. And I don't know if you remember, but you're always you always made me feel like you're really interested in what I'm working on and excited about the demos, and also just an inspiring leader of C-Cell. So thank you. And Marco, thank you also for joining my committee. Your feedback was really helpful, but also your work just inspired so much of what I've done in terms of showing that sim-to-real can work on these robots and building lots of infrastructure that I used during my PhD. So thank you. And finally, to Pulkit, thank you for being an amazing advisor. I think you really created a lab environment where I was able to pursue the research that I'm interested in and encouraged to kind of take risks and not just go for some low-hanging fruit. So this PhD wouldn't have been the same without you. And with that, maybe I'll since I'm over time, I'm just going to conclude and take questions. So thank you.
Any questions from anyone? Can you use the mic?
Hi, thanks for the great talk, Gabe. So my question is, with the soft mimic work, do you have a metric comparisons of a stiffer version of that mimic policy versus the soft mimic, and basically checking the tracking accuracy of both? What do you think you lose in terms of tracking accuracy with a softer policy?
Oh yeah. So we did check. We did compare the tracking accuracy of soft mimic versus training without compliance, and we found that there is a slight degradation. You can find the exact numbers also in the paper.
I see.
I think it is a slight degradation. It's not a huge one, but I think it is it could be a deeper question. So I think one thing that might happen is that the policy could become more sensitive to the sim to real gap and uncertainty in the model. And if there's some uncertainty in the model, then it might have to pick between bias towards better tracking or better compliance. Yeah.
I see. Cool. And second question is during the data augmentation step, do you also annotate the data with like the specific stiffness?
Yes. So we do. Um, yeah, and it's actually necessary the way that we do it, only because typically the displacement would only depend on the force, but we actually also have in the IK solver a term for regulating the center of mass. So then yeah, I guess we need to know both the force and displacement to get the solve, and that determines the stiffness.
I see. Cool.
Yeah.
Yeah. Great work.
Thank you.
Any more questions from anyone?
I have a question. Can you hear me?
Yes.
Yeah, awesome presentation. So for the compliant control, I assume if you kind of are applying a force or a torque on the robot at some point, like pulling it down, you could say, it has to make a decision at some point whether to like continue complying or to kind of exert a reactive force to prevent it from falling over. So how does it kind of determine what to do in that situation?
Oh yeah, good question. So in soft mimic, we're really training the policy to have a local compliance. So uh, it's being compliant around some reference motion, but it's not going to do like broader replanning. So for example, if you pull the hand, you keep pulling it outside of the robot's workspace. It's currently not going to replan and like take a step towards you. So yeah, it's not really specified the way that we've trained it right now. It might resist with a higher force, or it might tip over. But yeah, I think like our hypothesis was that local compliance is sufficient for a lot of tasks, and that's what we found. But it would also be really interesting to look at more global like interaction between global planning and local compliance. Yeah. Yeah. Oh, also, I think if anyone's interested afterward, Michelle and Vinky also are setting up a demo of the compliant control. So you're happy to go shake the robot's hand if that's interesting. Yeah.
Yeah. And I guess before we, close the room for thesis questions, maybe I'll have a little bit more to share. So if I can just plug in. Any questions for Gabe while I plug in? No questions. Gabe, you gave a good talk. You explained everything extremely well. So I just have, a few more things to share about Gabe as we are, wrapping up the Q&A. And this is really a journey that we have had together. And I was trying to look through my album while I was sitting, even in the past. So Gabe joined in February 2020. So that was just before COVID. So, the first photos I have is this of us, sitting with the MIT mini cheetah. And I think Gabe was working throughout COVID, when MIT was closed to get the robot to work. This is, was one of Gabe's birthday when we got the cheetah cake. So if you look at the cake, it has our project imprinted on it. This is one of our retreats. I think most people on this screen are now graduated. I think, Gabe, you are the last or the first batch of my students who is graduating. This is when Netflix came along and we were setting up the demo for them. This is when they really wanted to get shots of simulation, but I guess Gabe didn't want them to. You were too keen to show them the real robot. This is what would happen once you would go outside the lab, just trying to get the robot to work. With some work, it would, go up and, it would finally be on top. Here is, packing my car with stuff before we go off on a retreat. and I'm like always late. This is, our dribblebot project. I think the first testing we were doing outside the data center. This is when I managed to convince a few people to come and play Ultimate Frisbee, which is super fun, I guess, in the fall. And I guess one of our goals was that one day a soccer robot would play with us. So, Gabe, are we close to that? Closer. I guess this is the oral that Gabe gave in New Zealand, in Auckland. This paper has become one of the de facto standards for people wanting to use Unitary at this point. And this is, me and Gabe loitering in Auckland at like 10 p.m. talking about why depth is evil for robotics. This is, visitors coming in, and this is, Sam Gershman's kid, trying to control the robot. It has become easier and easier to control these robots. This is a day in the lab with, Gabe and Gabe's lab. This is when Nolan showed up. This is, I think, one of our, events. And this is one of the late nights when we are getting, I guess, Indian food and trying to prepare our paper. This is maybe, Gabe, your happiest moment. Picking apples. This is another retreat. And so many fun memories of, having you, Gabe. So it's been an absolute honor and pleasure to have you in the lab. And we're going to miss you if the committee decides that you can graduate. We could keep him. And I guess after that, it might look like this, but I hope we can keep it to this, Daniel, as you're saying. So with that, let's give Gabe a big applause.